This episode of CppCast is sponsored by BackTrace, the turnkey debugging platform that helps you spend less time debugging and more time building. Get to the root cause quickly with detailed information at your fingertips. Start your free trial at backtrace.io/CppCast. And by JetBrains, maker of intelligent development tools to simplify your challenging tasks and automate the routine ones. JetBrains is offering a 25% discount for an individual license on the C++ tool of your choice. CLion, ReSharper C++, or AppCode. Use the coupon code JetBrains for CppCast during checkout at jetbrains.com. Episode 116 of CppCast with guest Olivier Giroux, recorded August 31st, 2017. In this episode, we talk about CppCon open content and STL cookbooks. Then we talk to Olivier Giroux from NVIDIA. Olivier talks to us about his work on Volta and programming for it with C++. Welcome to episode 116 of CppCast, the only podcast for C++ developers by C++ developers. I'm your host, Rob Irving, joined by my co-host, Jason Turner. Jason, how you doing today?
Good, Rob. So we can keep saying that despite Jens's comments last week?
Well, we haven't heard of any new podcasts yet, but yeah, we do encourage, if you're out there and have any interest in starting a podcast, there is room for more in the C++ community.
Yeah, we might have to change it to say someday the only English language one or something. We'll see what happens.
Yeah, I'll see what happens. You know anyone down in Texas? Everyone okay with Harvey that you might know, Jason?
I don't know anyone directly who was affected, so I honestly haven't been watching the news a whole lot because I've been busy getting ready for conference prep stuff.
Yeah, I don't think I know anyone personally, but if any of our listeners are down there, I hope you're okay with the storm.
Yeah.
Well, at the top of every episode, I'd like to read a piece of feedback. This week, I'm going to butcher this name. It's coming from a listener named Wojciech, maybe? But he writes in, thank you guys for such a great podcast. For me, podcast is not only C++ news, libraries, but also a passion. Because of your show, I don't only write code, but I also started to love C++. Thank you guys. I hope you will never stop recording C++ podcasts. And also a separate thank you to Jason for the great C++ Weekly. So yeah, thank you for the feedback, and I'm sorry for horribly mispronouncing your name.
Yeah, thanks. That was great.
Yeah, and we'd love to hear your thoughts about the show as well. You can always reach out to us on Facebook, Twitter, or email us at feedback@cppcast.com, and don't forget to leave us a review on iTunes. Joining us today is Olivier Giroux. Olivier has worked on 8 GPU and 4 SM architecture generations released by NVIDIA. Lately, he works to clarify the forms and semantics of valid GPU programs, present and future. He was the programming model lead for the new NVIDIA Volta architecture. He is a member of WG21, the ISO C++ committee, and is a passionate contributor to C++'s forward progress guarantees and memory model. Olivier, welcome to the show.
Thank you. I'm glad to be here.
How did you get started working on GPU stuff, Oliver?
Oh, I had an internship with Microsoft one time, and then I had just come back from that, and NVIDIA's lead architect came and visited my school, and I'm one of the few people he interviewed there on site, and then they gave me another internship, and then I just never left. It's basically been 15 years now. So I like it.
Wow. That's pretty cool.
Yeah, well, we got a couple... Oh, go ahead.
Oh, I was just going to say, when I joined back then, all the interviews were, they were all graphics, right? NVIDIA didn't do anything other than graphics. And, so I remember doing vector algebra and projecting, primitives, projecting triangles onto planes and doing intersections of surfaces and other things. And, it was tough. It was really tough. It was like an 8-hour thing, back then.
Wow. Yeah, I would be out of my league. My geometry and my 3D geometry skills are not up to that for sure.
Well, Oliver, we got a couple news articles to discuss, and we'll start talking about the work you've been doing recently at NVIDIA. Okay?
Yep.
Okay, so this first one is an announcement from the Visual C++ blog. Their 15.4 pre-release is out, and in it there's going to be support for Linux development with CMake, which should be pretty exciting. You're already able to do Linux development from Visual Studio, but you had to create a Visual Studio project for it, which is kind of weird. But now the CMake support that they had for Windows is being extended to support Linux development as well.
It's not explicitly mentioned in here, but it talks about setting up a remote Linux target with a connection manager. And it doesn't explicitly say how easy or hard it is to do that with the Linux subsystem for Windows.
I believe it can be done, though. If you have a Linux subsystem, you can use your own Windows box as a Linux server, yeah. But yeah, they don't go into that explicitly.
That's, I was thinking somewhat cynically before our episode here that, I love Linux. I use it for most of my development. I run Windows everywhere. My real problem is when I need to port to Mac OS. I need a Mac subsystem for Windows that I can just easily connect to with Visual Studio or whatever, and then I don't have to ever boot my Mac box.
I am sure Windows or Microsoft would be happy to do that, but I think Apple would sue them if they ever tried to. But yeah.
Is this anything that you work with at all, Oliver, Visual Studio in your work or in these tools?
Oh yeah. I've actually been a bit of a black sheep in the architecture team here for always insisting to work on Visual Studio. Visual Studio pretty much got me started with C++ actually. So, in fact, it's funny because you're talking about Linux builds from Visual Studio, and that's been my day-to-day experience at NVIDIA for 10 years now, because 10 years ago, we wrote a tool that ingests VC project files, and then spits out a make file.
Oh wow!
And so we actually the NVIDIA architecture team has been many of our builds, those that are not silicon builds, obviously, but most of our C++ builds are enshrined in VC project files as their canonical build specification, and then obviously that works natively on Windows, and then we use our tool to convert to make files and make on Linux. And yeah, so that's been my normal thing, moving between Windows and Linux 10 times a day.
So have you guys considered moving that stuff to CMake or Meson or any of the other tools that would automatically generate the various build targets for you?
Well, one thing that stopped us from doing that in the past is we really wanted a native experience in the sort of the WYSIWYG part of Visual Studio. Tweaking a build in Visual Studio is really easy. Right click on this project, add an option here, click OK. And it's very self-discoverable. You don't know what the options are a priori? Fine. Open that properties dialog and then see what the options are there, and then click on the combo box and see what the values for this thing are. And in comparison, most of the other build tools assume you're already a build ninja, and you know everything you want to do. And that's not for many people who are here doing GPU architecture. That's not their bread and butter. That's not what they do. And so they kind of want a build system that gets out of the way and is easy to use. So Visual Studio fit the bill at the time. Now, it's not to say that, this is just like VI and Emacs. That's not to say that this hasn't been a subject of hot debate for that 10-year period, basically.
Yeah, I'm sure if you were starting from scratch today, you probably wouldn't roll your own solution, maybe.
Probably not, no.
And to be fair, I was just working with Visual Studio CMake integration, and getting started out of the box with the CMakes build folder is just like trivial, just works. But as soon as you want to change any of the configuration options, it seems to be very non-obvious how to do that. They have not integrated it with their GUI or anything yet, but their CMake integration is definitely getting better.
Okay, this next article we have is an update to SourceTrail, which is some software we talked about a while back. How do they describe this again, Jason? It's more of a source explorer. It's not an IDE, right?
It is not an IDE. No, I actually have played with it a few times since when they first mentioned it to us, and then with just this release also.
Yeah, it looks like the main new feature of this release is interactive tooltips, where if you're hovering over something, it gives you the full signature of that function or method or whatever it is you're looking at.
Right. It's a pretty darn neat tool. Did you play with it at all, Rob?
I don't think I have yet.
Okay. It gives you this great flow chart of what your code, what functions are calling other functions, and you can click on it and expand, and it shows you the source code and does mouse overs and hyperlinking between everything. It does a really good job of it, but I think more interesting than, just the fact that you can do that is it also shows you what templates are instantiated in many cases. And then you can get slightly more detail there about the template stuff that's happening, which I like, because I tried browsing it with TriScript, which has many template instantiations, and it does a pretty good job of keeping up.
Right. Yeah. And this next one is calls for lightning talks and open content at CppCon. And I'm not sure if we've mentioned this before, but this includes an announcement at the bottom of the post saying that all content is going to be free on Friday of CppCon. That's including the plenary speaker, Matt Godbolt, and all the other sessions that day.
Oh, I didn't even see that. I didn't even realize that was in this announcement. Yeah.
So yeah, if you're in the Seattle area, weren't planning on going to CppCon already, but you want to go check out some of the sessions, you can go and do so for free on Friday.
It'll be really interesting for those of us who are there for the whole week to see just how much busier it gets on Friday or not, or what happens with that.
I mean, there's plenty of, tech companies in the area employing C++ developers, so you think there'd be some people interested in that. You got Microsoft and Amazon right there.
Right.
But yeah, in addition to that, lightning talks and open content, they're now looking for submissions for that at CppCon. And the open content, those are sessions during lunch and breakfast, I guess. I don't recall that from last year.
Yes. Yeah. They're at various times during the day, not normal track sessions. And it does explicitly say again this year, open content does not require conference registration. So anyone can present, anyone can attend open content sessions.
Right. And then the lightning talks are 5-minute talks that are usually in the evenings. I think they do that for 2 or 3 nights last year. I'm not sure if that's the same plan for this year or not.
Right. I will say 2 years ago, I gave an open content session for the fun of it when I was giving also regular session that year. And it is so much less stress because the camera's not recording. And so if you wanted to try your hand at speaking at a conference, you didn't get a submission in for CppCon, try an open content thing. There's less pressure to get accepted, less pressure when you're actually up there talking.
Yeah. Okay, and then this last article, C++ 17 STL cookbook book review. And this is a new book that is just released from, I'm going to butcher this name too, Jacek Galowicz, I think. And it's over 90 recipes that leverage the powerful features of standard library in C++ 17. And the review is making it sound like it's a pretty good read, good book. And if you are interested, the author of this blog has managed to get, I think, 5 copies of the book that he's going to give away if you're interested. And you can register at the bottom of this post for that.
All right. Did you look at this one also, Oliver? Any comments?
Yeah, I looked at that announcement. Obviously, I zoomed straight to item 9, the SD1, my bread and butter. I might slightly prefer if people used stood async a little bit less. That's probably the SG1 PSA there. We're still working on that. Yeah, no, I mean, seeing the parallel STL, come to life, that's really exciting. We worked on, that was a lot of new, standard E's added there. We worked hard on that.
I am still looking forward to being able to actually try that in one of the standard library or standard implementations, if you will. Last I checked, GCC nor Clang was able to do parallel algorithms yet, anyhow.
Should be coming soon, right?
You would think.
Yeah.
Well, I've noticed a lot of the people who work on that, making noises through reflectors or IRC channels or sending email to one another. So, asking, how did that work? How did you manage to parallelize that?
Right.
And, what's the performance like and all that. So it's clearly being worked on.
Yeah, I've seen a handful of tweets from the Visual Studio team in that regard also, with a couple of comments that there's a couple of algorithms that no matter what they did, the parallel version was slower than the linear version, so they were going to, recommend against using those ones. I don't recall what the details were, though, unfortunately.
Well, it's perfectly valid to, stood par communicates information from the programmer to the implementation that were the lambdas passed to this algorithm invoked in parallel, they would not introduce data races. And then it's up to the implementation to decide what to do with that, and running it sequentially is perfectly valid. There's no rule that says if you pass in stood par, it shall run in multiple threads.
Okay.
That's not in the standard.
This is, please, I think that it would be a good idea, and the library implementation's up to saying, no, it really wouldn't be a good idea.
The way that I see it is you're communicating semantic information.
You're saying it's possible.
It is possible, yes. The program would not become undefined if you parallelize this.
Okay.
Which is the case for, a normal algorithm, a normal sequential algorithm. The lambda can do anything. The lambda is allowed to read and write any, C++ object. And the memory model says if you have multiple threads and more than one is writing, or one is writing and another one is reading, then you have a data race and your program's undefined. So the implementation cannot just go in and say, I think I'm going to run this on the thread pool now. It would have to prove the absence of aliasing between the references of different invocations of the lambda, and we all know that alias analysis is hard, and it's particularly hard in C++.
Right.
So this sort of automatic parallelization doesn't happen, but once the user tells the implementation that there would not be any data race in the case of par, and in the case of par and seek, you're saying further, not only would there not be any data races, but this code does not assume forward progress guarantee beyond lock-free. So then you can also vectorize it, also without any further proof.
So from your standpoint, would you suggest that when C++ 17 is fully out there, we all go and look at our usage of standard algorithms and mark them par and seek where we know it's a correct and valid thing to do, and then just let the implementation do what it wants with it? Or should we only do that if we're trying to optimize our use of the standard algorithms?
So in general, my first advice would be, you should always tell the implementation, as much semantic information as you know.
Okay.
And the implementation can, be clever about that. Especially as, and we're going to get to, we're going to talk about this in a few minutes probably. But especially as the variety of implementations increases, you should not prejudge, what the implementation might do with that semantic information. More information helps the implementation. Okay. Now, this said, before executors land, which is the case of C++ 17, which does not have executors, before executors land, it's difficult for you to apply constraints on top of that to say, well, here's the semantic information. This would not introduce any data races, but I don't want you to spin up 100 threads to run this because I know that this would thrash my system because something else is happening. So my first advice is give the implementation as much semantic information as you have, and then I just need to dither on that a little bit. It might be that for some number of years, doing that would be a de-optimization.
Okay.
and then in that case, as you optimize, you may want to roll it back. Leave a little comment in your code. To do C++ 20, add executor here.
Having a hard time porting my stuff to C++ 17 right now. It's hard to think to do C++ 20 while I'm at it.
Okay, Oliver. So your talk at CppCon is titled Designing C++ Hardware, and your abstract says you can run C++ on any computer you want as long as it pretends it's an 80s computer. What do you mean by that exactly?
Yeah. So the first thing is I want to get your attention. But I have a real thesis here, which is that C and C++, and CPU designs are, sort of in orbit of one another. They're kind of a binary star system. And, that really limits how much freedom, people have to go and make radically different designs. CPU engineers, so, people working on C++ look at CPU specs and they say, oh, this is, we have this feature and that feature. What can we do with that? Well, I want to peel the curtain and tell you that there's people on the other side who, are doing the same thing in reverse. They're looking at the languages and they're like, oh, well, but this language, it needs this. And so we can't build our design that way. Then we need to make this other change. We need to add a layer of emulation on top of whatever we were truly intending to do. Because if we don't have this layer of emulation, then C++ would keel over. And there are things that are not getting done. Like there are things that are not done, that are not built. There are things that people talk about that don't get built because it's too much risk. It's too much risk to depart from the quote canonical design, and so we'll talk about it and we'll say, well, if we spend 5-10 man years building this feature here, and then we really don't have much of a story for how it could work with C++, then it gets killed at some point. I mean, legitimately, we say, no, we can't do that. It's, we can't pin $1 billion design on a feature that might not work with the language.
That's interesting. So does it, you mentioned C++ specifically, but really this applies to, I guess, all compiled languages are all kind of similar in what they can do, right?
Well, I think it may surprise you to hear that Fortran is better at this.
Right.
Well, in part because we don't have massive operating systems written in Fortran today, so it's not too much of a systems language. In the systems languages, the machine has sort of leaked up. The abstractions don't hide the machine very well, and so you can see it better from C and C++, and that makes them a little bit more constraining. Yeah, I mean, in theory, it does apply to all to all languages, but pointers of all kinds, function and data, certainly apply the most pressure on the design.
Okay. Well, then I guess that you've been working on the NVIDIA Volta, and you're at least implying that it doesn't pretend to be an 80s computer. So how does it differ?
Actually, I would say it has a very clever way of kind of looking like an 80s computer, if you squint at it, but it really is not internally. So the main thing was, we started back when we started Volta. Here's the mandate that we started with. People think GPU programming is hard. You go on Google and you start typing, CUDA programming, and then the little autocomplete comes in, and then the autocomplete is hard, things like that. And, so we said, okay, well, we need to make a list of sort of the biggest problems. And, we knew for a really long time, the disjoint address spaces was a very big problem. 80s computers have flat address spaces. Memory is all uniform, is all one pool. It's all one pool. It's all flat. You can reach all of it, from any of your threads. So we knew that, and we've been working on that for years. Actually, Pascal, the architecture that comes before Volta, moved the needle quite a bit on, what memory you can address. But then one of the next things down that we ran into was, what can threads do? Like, what kind of code can threads run? Where we've been talking about GPU threads. I don't even have another word for it. We've been talking about GPU threads being threads, by definition. But there was code that they couldn't run. Like, you could go on Stack Overflow and, search for, writing a mutex. And I'm using a mutex as just an example of a concurrent algorithm. Okay. If I put my SG1 hat on, the issue here is the distinction between lock-free programming and starvation-free programming. A mutex, is a starvation-free algorithm. And GPU threads had a really hard time running that. And it's because they're more like vectors. They're more like SIMD underneath, okay. Deep in the bowels of the machine. They're running on SIMD. Mm-hmm. But that was shining through all the way up, through the execution model. And then these threads they could deadlock, when they were trying to execute a mutex algorithm. So in Volta, we looked at that, and then we wondered, can we build a different kind of machine? Can we build a machine that has the same efficiency at the bottom, but runs all C++ concurrent algorithms, bar none, at the top? And that had not been done. That had not been done before. You can look around, and GPU-like threads have existed for quite some time. In the 80s, I don't know, you probably don't know this. Pixar was a hardware company. Okay. In the 80s. And they built their own machines. And they're sort of the first example you can point at of somebody building, the same kind of threads that we've been building. And, across this 30-year time span, nobody had managed to solve this problem. So anyway, in Volta, we set out to do that, because we wanted to be able to run, basically anything a std thread can run. That was the goal.
So I guess maybe we should just take a quick step back and describe exactly what Volta is. Oh,
it's a GPU. Okay. Well, first of all, Volta is an architecture. Volta is the name of the architecture. So it's a family of GPUs in some way. You've only seen one today. We launched it this spring. Actually, I was on stage at GDC, launching that in the spring. The first implementation of Volta is V100, and V100 is a big chip. It's a really big chip.
You guys just go right out the door with version 100. Most people start at like 1.0.
Well, actually, we have a naming scheme at this point. I mean, you could go on Wikipedia. It's pretty amazing how NVIDIA doesn't really communicate, internal product numbering, but somehow Wikipedia always figures it out. There must be a mole or something. We'll in our current nomenclature, we'll have a 2-letter prefix, and then we'll have 3 digits, and 100 is the big one.
Okay.
100's the big one, and then we then that third digit down at the bottom, 2s are just about as big, 4s are half of that, and then 6s are half of that, and then 7s are half of that. And GPUs have a big dial on how big or small you make them. We'll have in the same family something with 80 SM cores, and then we'll do one with 40, and then one with 20, and then one with 10, and maybe one with 4. It's a big range. Anyway,
it's a GPU architecture that's just been released, basically.
That's right. Yeah, that's right.
Well, sorry, I didn't mean to cut you off if you were going to go into more detail there.
No, actually, that's a good idea. You should you should try to keep me help me be concise.
So this is not something that's specifically designed for computation. It is something that we could buy in our desktop graphics adapter next time I go to upgrade my machine or something.
Right. So at some point you'll be able to.
Okay.
At some point you'll be able to. Right now V100 is going out in big HPC boxes.
Okay.
V100 is what the Department of Energy bought for Summit and Sierra. Two big supercomputers coming online.
Where are those two going? Do you know?
Oh yeah. Summit is going to Oak Ridge National Lab.
Oh, okay.
And Sierra is going to Lawrence Livermore.
All right.
Yeah. So these machines are going to be working on both open problems, like climate change research, modeling of aerodynamics of things, and combustion efficiencies in engines, and they'll be working on galaxy collisions and things like that. So big machines, cool stuff. So V100 is going in there right now, and it's also going into a lot of deep learning systems that are going out, already out, soon going out. I'm not sure what the right timing is.
So from the C++ programmer's perspective, now, how does programming Volta look different than programming with Cuda?
Oh, so Cuda is your vehicle. I mean,
okay.
I think, I might even say, expand that term a little bit. Call it Cuda C++. Cuda C++ is a C++ product, similar to Visual C++ is a C++ product.
Okay.
Okay.
Now Cuda C++, is, and I won't hide it, is the least conforming, of all the C++ products out there. But probably Visual Studio 6.0 was more conforming than we are, at the moment. But it's actually, now that I've said that, I think you'd be surprised just how conforming it is.
Okay.
On the language side, there's very little that you can't use on the device. In fact, in the last month, I've written a ton of Cuda, way more than I've written recently. I've been waiting to get my hands on a V100 to write a lot of Cuda code. So I finally did. Finally got my own. Sorry, I get them ahead of you. And I've just been typing. I have been typing for 2 months, basically. And my own surprise was, I have not had to think about, can I use this language feature? I've been writing in C++ 14, in Cuda C++, and fundamentally, the only thing where it's obvious to me that this isn't your regular conforming C++ implementation is that you need to prefix all your functions with a device keyword.
Okay.
That's pretty much it.
Interesting.
So is Cuda C++, did that come out with Volta, or has that been around longer?
It's been around for 10 years, man.
Oh, okay. My mistake.
10 years, yeah. And you don't need to clone a GitHub repo and make it yourself. You can download it on our website.
Okay.
But the capabilities have changed with Volta.
Right. We have this concept of compute capability level.
Okay.
And Volta is compute capability level 7. And so what that means is it can use everything that was in 6, which includes the unified address space with the illusion of coherence, at least. And it adds to that 2 really key things for C++ developers. Number 1, it adds a conforming primitives that are compatible with the C++ memory model. And second, the forward progress guarantees, which allow you to write just any concurrent algorithm you want.
Okay.
I wanted to interrupt this discussion for just a moment to bring you a word from our sponsors. BackTrace is a debugging platform that improves software quality, reliability, and support by bringing deep introspection and automation throughout the software error lifecycle. Spend less time debugging and reduce your mean time to resolution by using the first and only platform to combine symbolic debugging, error aggregation, and state analysis. At the time of error, BackTrace jumps into action, capturing detailed dumps of application and environmental state. BackTrace then performs automated analysis on process memory and executable code to classify errors and highlight important signals such as heap corruption, malware, and much more. This data is aggregated and archived in a centralized object store, providing your team a single system to investigate errors across your environments. Join industry leaders like Fastly, Message Systems, and AppNexus that use BackTrace to modernize their debugging infrastructure. It's free to try, minutes to set up, fully featured with no commitment necessary. Check them out at backtrace.io/CppCast. So what was your role during the design of Volta?
So I was one of the leads in the SM core. The SM core is the execution core inside of the GPU. And for the most part, I focused on these 2 things here. I focused on the memory model and the execution model. I have a fairly long history of working on the execution side. 7 years ago, I wrote a prototype in microcode for Kepler GPU that had this forward progress guarantee. It was incredibly slow, but it sort of proved out the idea. People were not thinking about it as much. People were thinking that this was just how it was. GPU threads couldn't run concurrent algorithms because obviously, and then you'd approach them and you'd say, well, we can work on that. And they're like, oh yeah, but the performance would never be good. But the area would be too big. It would be too many transistors, or it would burn too much power. And, so we had to chip away at that until eventually, everybody said, well, it's just plain better. So let's do it. Yeah. So 7 years ago, I did that first prototype that showed that it was doable. And then I followed through.
So would it be fair to say that you specifically designed Volta with C++ in mind to be able to target it?
Oh yeah, absolutely. Yeah, absolutely. I quoted paragraphs out of the C++ standard, in specs and in internal communication. The definition of forward progress in C++ is rather well crafted, actually. And it's even better crafted in C++ 17, the SG1 PSA here. We've done a lot of work to add, different kinds of forward progress guarantees and clarify the language. But, even back in C++ 11, there was, useful stuff in the spec. In particular, the definition of what is a visible machine step. That was really key. So I quoted that out of, what used to be, clause 1. So there was that. And then the second thing is on the memory model side, we also, stole as many good ideas as we could out of C++. I have a lot more to say about that if you want to drill in.
Sure,
Yeah,
go ahead.
for it.
Oh, so on the memory model side, I think C++ 11 was one of the biggest gifts ever given to processor designers, honestly.
Interesting.
Yeah. I mean, before C++ 11, the state of the art was everybody used volatile.
Incorrectly.
And yeah, well, right. And approximately no one can correctly describe the semantics of volatile. And in part, it's because, caveat, it doesn't have any semantics. It's crack open your CPU manual, and then the semantics or whatever that other thing says. And so people would come to us with code that they had written on x86, say, and they'd put volatile in there, and and then they'd say, well, we expect you to run this. And as a processor designer, this is awful. You're basically asking me to be bug compatible with x86. Like, if you use volatile, then your code rests directly on the metal. And then the semantics of your code, or whatever the semantics of the metal is, bugs included. Mm-hmm. And since concurrent programs are very difficult to debug, and the bugs in concurrent programs can be latent for a very long time, they just don't activate, then if there's a bug in your code that x86 did not activate, because it has an extremely strong execution and memory model, then you coming to me and saying this code with volatile needs to work is basically saying I need to build an x86 now, which I'm not allowed to do. So then C++ 11 comes along, and now there's a memory model, like a spec you can read, and it's a relatively portable spec, and there's some really good ideas in there. The C++ 11 memory model is based on work by Sarita, a paper she wrote in, I think, 1990, introduced a model called DRF0. And the DRF0 model says, if you can split all your memory accesses between synchronizing and non-synchronizing, then you make the synchronizing one sequentially consistent, and she can prove that there are no non-sequentially consistent executions left. But here's the good news. The synchronizing accesses is like 1%, and the non-synchronizing is like 99%. And the non-synchronizing accesses, they don't have any expectation of memory consistency between threads. Any expectation at all. In fact, the non-synchronizing accesses don't even need coherence. Now, think about that. CPUs don't know the difference between these two things today. Like when you JIT or compile to x86, you do a bunch of reads and writes. Mm-hmm. x86 assumes every last one of them is synchronizing.
Okay.
Even though 99% of them are not, and the 99% that are not don't even value the coherence protocol that x86 is running.
Okay.
So 99% of the effort being expended by a cache coherent CPU design is not providing any value whatsoever. It is warming your room ever so slightly. And occasionally depressing your performance, because it needs to assume everything is always synchronizing. Yeah. Okay. So that's one of the big things we did. We looked at the C++ 11 memory model, and immediately everybody here realized, oh my God, we can take this distinction between atomic and non-atomic in C++, matching to synchronizing and non-synchronizing in DRF0. We can take this information, this high-level information from the program, and give it straight to the silicon. Not only carry it through compiler optimizations, but actually give it to the silicon. And then the silicon only needs to make the atomic XSCs really appear coherent. The non-synchronizing XSCs don't need any coherence whatsoever up until, up until the acquires and releases. But then at that point, on an acquire and a release, you can put a fence there. And so you can recover coherence at that point.
It's really interesting. And I'm trying to process it all because if you're doing multi-threaded programming correctly, you can never assume that the threads are synchronized, as you're saying, right? So, or the data between them is synchronized, unless you have some sort of a fence or an atomic or something that you check on, right?
Right.
So you don't have to do any of the coherency until you see one of those fences that would force that to happen.
Exactly.
Effectively.
Exactly.
So do you anticipate, not that this is, necessarily your expertise, but that general purpose CPUs will take advantage of this more at some point?
It's really tough for them. It's really tough for them because they have spilled their specs all over the interwebs. They have backwards compatibility requirements placed on them.
Right.
That makes it so, design decisions they made in the 80s, constrain what they can do in the 2010s and 2020s. Very much so. And x86 must run x86 code because the day that an x86 stops running x86 code, they lose their stickiness. Right. So that is massively important to them. Other processor architectures get to occasionally make a break, but very occasionally. So, even in the case of ARM, we like to think that ARM is this new upstart somehow, but they are totally not.
They're from the 80s also, yeah.
They are also from the 80s, yes. So it's tough for other for other processor teams to be able to exploit this. Yeah, and one more thought, so I didn't mention IBM. IBM Power, which is an awesome, badass product that unfortunately too few people get to experience. But they have huge reliability requirements placed on them. The power system needs to be resilient in the face of the kind of errors that will make your MacBook Pro just, crash. Your laptop will just panic and reboot and you'll go like, my computer crashed. It happens. Right. That does not happen to an IBM Power, basically. It cannot happen. So they have reliability features in there that force them to be clean of any possible memory error before they can execute past a certain point, right?
Okay.
All right, and that affects how strong their memory model can be. Now, I use the word strong and power, which would make some people glitch, but yeah, the IBM Power is a stronger memory model than my machine. So
that's right. I don't know enough about it to nitpick anything that you just said, so you're good here.
So we've talked a lot about what you can do with C++ and Volta. Are there any limitations worth pointing out?
Yeah, so we're not done. So I said a little while ago that that Cuda C++ is both surprisingly conforming and also the least conforming implementation. You can hold both in your head at once. Now, what's remaining in our conformance? Some of those things look more durable than others. You can imagine. So with Volta, we tried to make significant progress on the top things. We're not done, so we're still thinking about this. We're still working on these things. Yeah. So the things that are easy or hard. Well, concurrent with development on Volta, there was development on C++ 17. And in C++ 17, we clarified the nature of forward progress to include 3 different progress guarantees. There are 3 different levels, tiers of progress guarantees in C++ 17.
Okay.
There's the concurrent forward progress where you launch a thread and you know from the time that the constructor of the thread returns that that other thread shall be making forward progress right now, and it will never stop. So you can launch a thread and then wait for it to write to an atomic, for instance. That's the concurrent forward progress. The parallel forward progress is slightly less than that, where you know that if it has started to make progress, then it will continue. But you don't know when it will start unless you block on it. And if you block on it, then you know it will start.
Okay.
And then weakly parallel is basically no guarantee of independent forward progress. So that's where that matches with par and seek, and that's where you can't write a mutex in that, for example. Okay, so concurrent with Volta, there was also a lot of clarification going into C++. I think that that's going to continue, basically. We're going to build another architecture. Spoilers! We're going to build another architecture. Now we're going to build another architecture, and we're going to fix some things that are in our conformance issues. But then we're also probably going to think about changes to C++ 20 that will make it much easier to implement. So, all right, what's in that list? Thread local storage is a big one. Back to this emulating 80s computer thing. Threads in C++ are assumed to be fairly heavyweight. Now, C++ is pretty well designed for a machine where the number of threads is like 12.
Okay.
Right. Yeah, 12 or I guess we'll go to 60 or something. It's pretty well designed for that. But some features like thread local storage, are expensive for systems that have lots of short-lived threads. Volta has 163,840 threads.
Wow.
All of which can run, all of which can execute anything a stood thread can execute. But except for TLS.
But
when
it sounds like you were saying that virtually all the variables are thread local anyhow, because it's not going to synchronize them unless it has a reason to.
No.
Am I being too pedantic or something?
Yes. So Volta threads can dereference any pointer.
Okay.
Anywhere in memory. So you can imagine, you build a box and you put 128 gigs of RAM on the CPU, and then you slot a Volta in there, and it has its own 16 gigs on it. Volta threads can dereference any of this, all of this, and they can synchronize. So you could use a moral equivalent of std-atomic, or hopefully very soon now, actually std-atomic. And when they synchronize, they have a view of memory that's compatible with the C++ memory model.
Okay.
So you just you write code as normal. Okay, but one thing that they don't currently have is access to thread local storage. So if you declare some stuff that's thread on the bar local, then only your CPU threads will get that right now. Now you can take a pointer to these things and then share it out in memory. Thread local doesn't preclude sharing. It's private by default. But if you take the address of it, you can share it. And then GPU threads will be able to see it and access it just fine. It's just that, using the name of the variable, accessing it by its name, will not work on the GPU threads right now. Now, I am not sure which way this one will land. The lack of conforming thread local, is not unique to us. In fact, if you look at even CPU parallel programming systems, they have a similar issue. I think one of the poster children is actually Silk from Intel. Silk, I'm going to say something good about Intel. Silk is really impressive work. It's really nice. It's fairly well reasoned. Now, in Silk, when you spawn children, and you block on them, the parent can be suspended and passed by continuation passing. And the children can steal the parent continuation. Which means that a child running on another thread can steal the continuation of the parent that came from, parents on thread 1, spawn some children, blocks on them, children run in thread 2, and then when the children in thread 2 are done, they steal the continuation of the parent, which now resumes execution on thread 2. Your thread local just changed. You used to reference an object. Now it's a different object. What does that mean? What does that mean? You could write a conforming C++ program that is highly dependent on all your thread local accesses being to the same object.
Yeah.
Because maybe you put some important data in there and you're going to get it back later, right? And now you're in another thread and it's not the same one. So this TLS issue is, I swear, SG1 spends 1 day per meeting talking about that. So we have to do something about it. The definition that's there right now is, very strong. Basically only works with stud threads and the thread that runs main. The thread that shall not be named that runs main. And as we move into more and more parallelism, we need to clarify what thread local means. Even if you ignore Silk and you stay in C++ 17, consider std_par and par on seek. If I run a parallel algorithm with std_par, then more than one of my lambdas will get the same TLS. But they'll get it in sequence. But they'll get the same TLS, which means that they can kind of, so it means you don't get fresh TLS every time. Did you expect fresh TLS? Did you expect that it would get reinitialized? It's not going to be reinitialized. Par on seek, multiple lambdas effectively share the same TLS. Because they might run in vectorized SIMD lanes. And when they read and write the TLS object, they're reading and writing the same one.
Right.
So they kind of have a data race. They could stomp on each other there. So I think you have to expect that in C++ 20 we're going to write something about TLS, and there's maybe similar to what we did with the forward progress guarantees, there's going to be more than one tier. There's going to be has full fat TLS, that'll be the thread thing, and then has potentially shared TLS or potentially identity changing TLS, and that'll be maybe the std_par thing, and then has no access to TLS, might be like the par and seek thing.
Wow.
And so what it'll mean for our future architectures here at NVIDIA is, we'll have to decide which tier we want to go for. In Volta and C++ 17, which were designed concurrently, which no one except people from NVIDIA knew, but, which were being developed concurrently, we decided to go for the std_par tier, even though everyone in the world expected us to build the par on seek tier. Okay, so what are we going to do with TLS? I don't know.
Okay.
Yeah. Well, I have to say, I don't know. So that's one challenge, and then there's a similar challenge with sharing pointers to automatics. I just said, thread local is private by default, but It can be shared if you take a pointer to it. The same thing is true of automatics. If you have a local variable, you can take the address of it and somebody else can read and write it. As long as and by the way, be careful because it's easy to run afoul of the memory model when you do that. But assuming you dotted all the I's, then you can do that. Well, you can't do that on the GPU right now. And that one's been really tough to think about. We have a super efficient implementation of stacks, and it's kind of incompatible with addressing. We emulate addressing for the thread that owns the stack, that particular stack. But it's tough to emulate it for all threads in the system. So this is a long answer to your question of what incompatibilities remain. Those are some big ones. Everything else probably that you can think of. I haven't said the word exceptions. I think too much ink is spilled on our lack of support for exceptions. I don't think it's a durable problem. I think it's a business question. Somebody needs to say, we want to buy GPUs and we'll only buy GPUs if they have exceptions. And then you have to say it with a straight face and not like burst out laughing in the middle of that sentence. And then it can be solved. It can be worked on. There's no reason GPUs can't do C++ exceptions. It's just control flow.
Right.
Okay. Well, it's been great having you on today, Oliver.
Oh, thank you. It's been great. I'm trying to get the word out everywhere that I can about the C++ stuff we did in Volta. You'll see me at CppCon. I'm working on blog posts and other things to put out that communicate straight to the users.
Where's your listeners look for that? On the NVIDIA blog or on your personal blog?
No, on the NVIDIA blog. We have a blog with a great name called Parallel for All. That although you might say it should really be parallel for each, but it is currently called Parallel for All. And that blog in particular has posts that are relevant to programmers and in general C++ programmers. That most of the articles are aimed at C++ programmers.
Okay. Thanks so much for your time today.
Yeah, thanks for joining us.
Thank you.
Okay. Thanks so much for listening in as we chat about C++. I'd love to hear what you think of the podcast. Please let me know if we're discussing the stuff you're interested in. Or if you have a suggestion for a topic, I'd love to hear about that too. You can email all your thoughts to feedback@cppcast.com. I'd also appreciate if you like CppCast on Facebook and follow CppCast on Twitter. You can also follow me at Rob W. Irving and Jason at LeftKiss on Twitter. And of course, you can find all that info and the show notes on the podcast website at CppCast.com. Theme music for this episode is provided by podcastthemes.com. CppCast.com. Theme music for this episode is provided by podcastthemes.com.